So the next topic we're going to cover here is to evaluate all the different concurrency and parallelism mechanisms available in Java that we've covered. And you'll see very quickly why that's a worthwhile thing to do, because we've been given all this capability, but we have to figure out which ones to apply and when. So the first thing to notice is that Java's concurrency and parallelism mechanisms span multiple layers in the software stack. And choosing which of these mechanisms in which of these layers to apply depends on various factors. There's really no one-size-fits-all solution. And part of your job as a professional in this field is to be able to make informed choices of the different mechanisms available, and then lobby your colleagues or your customers or your clients or whatnot as to why your choice is the right one to make. So if you're building performance-sensitive applications, let's say you're building some kind of a gaming engine and you're using Java, which does happen. In fact, if you take a look at some very popular gaming engines like Minecraft, which lots of people enjoy, you'll see that it's developed in Java for at least the desktop version. So people who are building performance-sensitive apps, or if you're trying to build kind of the infrastructure that people would use to build performance-sensitive apps, you may want to use the shared object mechanisms we talked about. And these would be the mechanisms that are part of the Java Util Concurrent package. If you want to learn more about what's in Java Util Concurrent and the design rationale behind a lot of the features there, take a look at the video down below by my friend and colleague, Doug Lee, who developed most of these libraries as part of the Java development effort over years. So examples of these things would be reentrant locks, Java atomics, the concurrent hash map, semaphores, condition objects. These are basically the core synchronizers that came into Java 5 in the 2005 timeframe. The good part about these mechanisms are they're very efficient, very lightweight, well-designed. So that's all good. So if you have to program at this level, you're going to find it very pleasant to use these features. The downside is that it's still somewhat tedious and error-prone to use these object-oriented mechanisms because you have to do a lot of the work yourself. Now, you can apply patterns and you can wrap these things up in frameworks and so on to make them easier to deal with, but somebody has to understand this stuff, and if you're programming at this level, you have to become an expert at synchronization and coordination. So as a result, shared objects and those layers of abstraction, or that layer of abstraction, which is devised to run on top of the underlying execution environment in terms of some parts of the Java class library, they're best used by infrastructure developers, people building the platform, as opposed to application developers, people building apps on top of the platform. So app developers typically need to be more focused on domain-oriented issues like user experience and user delight and providing features, whereas infrastructure developers are more about how do you take good advantage of the underlying operating system features and the hardware and the resources that you've got. So the low-level stuff, the shared objects, they're great, but most app developers don't really need to be aware of how they work. They can work at higher levels. If your job is to build frameworks, so if you're building something like, say, RX Java, or you're building something like the Android Async Task Framework or the Java Executor Completion Service or so on, then you may want to use the message passing mechanisms that are built into Java, the ones that allow passing of objects between producer and consumer threads, for example, like array blocking queue or link blocking queue and so on. So if you're a framework developer, and framework developers are building things, again, for app developers to use, you may want to use message passing. The good part about message passing is that it's very flexible, it's very decoupled. Producers and consumers don't have to interact directly. You oftentimes don't require the use of low-level synchronizers like mutexes or semaphores or condition objects. You just create a message in one thread, put it in a queue, and one or more threads will pick that message up and do something with it. So it's very flexible, very decoupled. The downside is that passing messages back and forth between threads can incur some time-space overhead, which may be undesirable. And the reason for this is that moving things between threads incurs higher context switching overhead, higher synchronization overhead, higher overhead for data movement, for memory management. for cache invalidation, all these other kinds of things that we sometimes want to ignore when we program in higher level languages like Java, but will in fact show up if you spend time systematically benchmarking your code. So tend to be very flexible, but there may be some costs associated with that. And if you're building infrastructure for performance sensitive apps, you might not want to pay that cost. Of course, it may not be a big deal in practice. As always, as we like to say, your mileage may vary, so make sure you benchmark things comprehensively. Now, if you're building apps, and in our course, we're building apps, we're building the image crawler app over and over again with different mechanisms. App developers typically want to use higher level frameworks. They don't really want to be bothered with shared object synchronizers. They often don't really want to have to think about spawning threads and passing messages. Those are concerns that are really below the radar screen or below the waterline for people who are trying to build apps with various cool features to delight the users. And so they're most likely to want to use higher level frameworks. And these would include things like parallel streams, completable futures, which we'll cover, RxJava, which we'll cover, Project Reactor, which we'll mention, but you won't get experience with because Android doesn't really support it. But the RxJava is basically the same thing. So as you can see, these capabilities are up the stack. They're part of the application frameworks layer as opposed to the kind of Java class library layer or the execution environment layer. So it's basically higher level abstractions. And the good part about them is it makes you way more productive once you understand how they work because you're working at a higher level of abstraction, leaving lots of details to be dealt with by the underlying frameworks. And it's also more robust because people have spent quite a bit of time building these abstractions and testing them and trying them out in practice and optimizing the heck out of them so they run very well. And you don't have to worry about all that low-level gobbledygook yourself. The downside, again, is there could be some additional time and space overhead relative to programming things at the lower levels. But of course, if you program at the lower levels, you introduce accidental complexities into your code, which makes it less likely to be correct and harder to evolve and maintain. And to some extent, some of these frameworks are a bit overly prescriptive. If you have a problem that fits well within the parallel streams model or the concurrent models for RxJava or Project Reactor, you're doing great. But if your problem doesn't quite match that, you're probably locked into a Procrustean bed that will make it hard to achieve your goals without standing on your head or actually incurring more overhead than you may want. The good news, of course, is that for most apps, this is not a big deal and it all works quite well. Something else to keep in mind here is if you want to be a so-called full stack developer, or you want to be someone who basically understands computation and software design and implementation and architecture and testing and debugging and so on at multiple layers in modern systems, which we sometimes call a full stack developer, then you should be fluent with all these different layers. So this class, as we've discussed, is really going to focus at these upper layer application frameworks. But by the time you're done being a student at Vanderbilt, wouldn't hurt to have a more comprehensive knowledge as well. There's more to full stack development than I'm showing here. Full stack development also means someone who can do the back end, server side, interacting with databases, and so on, interacting with clusters, doing microservices, as well as also handling the front end web development or native app development. Being a full stack developer these days is incredibly hard because there's so many layers to work on. So you're probably going to focus on, a subset of those, but it still doesn't hurt to have a comprehensive understanding of how things fit together end to end and top to bottom. So that's an overview of the different concurrency and parallelism mechanisms available in Java. I don't expect you at this point to know exactly what the details are of all these different things we've discussed. We're going to talk about many of them throughout the rest of the course. But what I want you to understand at a high level is the concept of layers and levels, and the fact that the lower level stuff is better for the more performance sensitive apps. But if you're building more conventional things, you can probably take good advantage of the higher level frameworks. And that's exactly what we're going to do in the rest of this course.